All right, this is problem 1 of homework 10. So here we've got an object sliding up a ramp. So there's the ramp. We know the object's path. It starts at the bottom, it slides up, and then it comes back down. So it's going to travel in some path like that. I'm going to label places in this motion as A, B, and C. We need some symbols for the various quantities that we're looking for. So this distance here, how far it goes up the ramp, I will call D. That's what I'm going to be solving for. And I'm also going to want to know the displacement in the y direction, which is d sine theta. That's theta. Let's identify a few things in the problem, give them variables. So 2 kilograms I will call m, 37 degrees I will call theta. This initial speed, since that's the speed at A, I will call v sub A. Now, one thing that I will need also to know is the frictional force. So we'll do that as a sidebar here. The frictional force we know is mu times the normal force. In thinking about how big the normal force is, so I'm going to sketch a quick free body diagram here. I know the normal force goes like that. I know gravity goes like that. If this line here is the slope, then I can decompose gravity into its components, one perpendicular to the slope and one parallel. Let me label those things I've drawn. That's the normal force. That's the weight force. This one that I want is going to be mg cosine theta. And since this doesn't move into or out of the slope, I know that the acceleration in the direction perpendicular to the slope is 0. This tells me that the normal force minus mg cosine theta equals 0. And that tells me the normal force is mg cosine theta, and thus the thing that I came here for, the force of friction, is mu mg cosine theta. So that's something that I will need when I do the work energy theorem. Might as well figure it out now. Then, for part A, use the work energy theorem to determine how far the block slides up the slope before momentarily coming to rest. This is from picture A to picture B, point A to point B. So let's solve the problem now. A, use the work energy theorem from A to B. So the forces here doing work are gravity and the frictional force. So I know that the kinetic energy at A plus the work done by gravity, it's going to be negative, plus the work done by friction equals the kinetic energy at B. And I know that that's 0 since B is the point where it momentarily comes to rest and turns around. So now I need to know the work of gravity and the work of friction. So the work done by gravity is going to be the force of gravity times the displacement in that direction, which is minus delta y. So putting that in, the whole thing is minus mg d sine theta, because I figured out earlier that delta y was d sine theta. The work done by, the work done by friction, that's going to be the force of friction times the distance moved. Here, friction is exactly opposite the distance moved, the displacement. So that just gives me a minus sign, and this is going to be the force of friction. So mu mg cosine theta multiplied by minus d. So now I can put all those things in. I have that 1/2 mva squared plus the work of gravity, which is minus mgd sine theta, plus the work of friction, which is minus mu mgd cosine theta equals 0. So the point of this part of the problem was to solve for d. So I can do that. That gives me d equals, so here I'm just going to, first let me cross out all of the m's. I can do that. This gives me, for d, 1/2 va squared, all divided by g sine theta plus mu g cosine theta. Now, this problem actually gave us some numbers. So I'm going to type those into the Google machine. So I have 1/2, you can't see this, but I'm typing into Google Calculator. 1/2 times the initial velocity squared, which is 10 meters per second. And all of that is divided by, I'm going to use 10 meters per second squared for g times the sine of 37 degrees. The coefficient of friction was 0.3, so 0.3 times 10 meters per second squared times the cosine of 37 degrees. And when I do this, this gives me 5.94 meters. Part B asks us now to think about the thing coming back down. And to do that, I just use the work energy theorem. Now, instead of from point A to point B, I'm going to use that. Now I have a choice. I can do it either from point A to point B or from point A to point C. I'm going to go all the way from A to C because that way I can be lazy. I know that gravity doesn't do any work if I come back to where I start. So you could do this from B down to C, that's fine, but I'm going to do it from A to C. So what this tells me is that the kinetic energy at A plus the work done by gravity from A to C, which I'm only writing this here so I can cross it out and say that it's 0, plus the work done by friction from A to C equals the kinetic energy that I get when I come back down. Now, the work done by friction is interesting. So friction does negative work both going up and coming down. So the work of friction in comparison to this, which is what we got on the way up, it's going to be twice that much. So minus 2 mu mgd cosine theta. The factor of cosine theta, to remind anyone, comes from the normal force. The distance moved is just d on the way up and then again on the way down. The factor of cosine theta comes from the normal force. So putting all of that in, I have 1/2 mva squared minus 2 mu mgd cosine theta equals 1/2 mvc squared. I can now cancel all the m's. And solving for vc, this is going to be the square root of va squared minus 4 mu gd cosine theta. But I know d, right? I have a value of d from my previous part. So all I need to do is to type this into the Google machine again. So I've got the square root of VA squared, so VA was 10 meters per second, that squared, minus 4 times mu, which is 0.3, times g, which is 10 meters per second squared, times d, which is 5.94 meters, times the cosine of 37 degrees. And when I put this into my Google machine, I get 6.56 meters per second. Makes sense? It slowed down on the way back down. So that is problem 1. Things to notice here. The work energy theorem, again, has this form. Kinetic energy in the beginning plus the work done by all forces equals the kinetic energy at the end. Also notice that we did need to draw a free body diagram up here to figure out the force of friction. You may not need to if you just remember how Unit 2 went really well, but you can. Another thing that, that was important to note is how we calculated the work done by gravity. Notice that the work done by gravity is the force of gravity times the displacement in the direction of gravity, so the vertical displacement.